Thank you, everybody, for coming. My name is Grygleski. I'm a developer advocate with the global Java developer advocacy team at IBM. And by night, I'm a Chicago Java Users Group organizer, as well as a few other IBM-sponsored meetups, too, in Chicago. So that's my background, and I actually was a developer, engineers, too, before, probably for over like 25 years or so. And I live in Chicago for about 15 years so far. So I'm here today to talk about reactive Java. And the topic, I'm naming it, this title, Reactive for the Impatient. So the impatient part, as I was coming with the title, I was thinking that, well, reactive systems are really meant to build for people like us. We are actually, by nature, very impatient, like we can't wait. So that implies a sense of like urgency, responsiveness. So that's how I picked this title, Reactive for the Impatient for us. And as such, too, first of all, before I go on to my next slide, so I just want to thank you to all the organizers and volunteers of GeeCON, and then also, too, the organizers has reminded me that everybody join the slido.com, and then enter this if you have any questions towards the end. Okay, so I'll go back. So the title of my talk, Reactive for Impatient, essentially, too, what I've also named the title to, I call it like a gentle introduction to reactive programming and reactive systems. And this is really for like a Java, basically it's meant to be for Java. But as such, too, the concepts itself, it really cuts across any language framework. It's very, very universal, the concepts. So I hope that, let's say if you are not doing Java or JVM, at this time you should still be able to follow up with that. So as such, too, I'll also step to give a bit of introduction to 4 popular Java tools and frameworks libraries, namely RxJava, Spring Reactor, Akka, and Eclipse Vert. So I apologize, too, if you find that the materials may be a little bit too much of a beginning. So please feel free, too, if you would like to go to something else, too. But as such, this really meant to be more of a gentle introduction. Okay. So first of all, we talk about like why reactive. So reactive systems, reactive programmings are not new, but as such, too, and like for the maybe past 5 to 8 years or so, this word reactive has become very popular. It's all over in the marketplace. And there's also a bit of confusion, too. I started working on reactive since I joined IBM about 8 months ago. So even for me, having been a developer doing traditional style programming, imperative programming, I found it to be confusing. There's also like React Native, and so that's JavaScript coming out of Facebook, as you are all aware. So as such, like why reactive? Why now? So basically, too. Whoops, why is it like going so fast? Sorry. Let me go back. We go back. I don't know. Maybe I pressed the clicker a little bit too fast. Okay. So as such, too, there have been like evolving changes in the marketplace. So hardware have really greatly improved, right? Now we have better CPUs and multi-core CPUs and hyper-threading and all these things, and virtualized computing infrastructures, cloud, and multi-cloud too, not just single private cloud, hybrid cloud, everything. So all of these, as well as actually the needs of humans, right? We have systems now that are more capable now, and also the fact that each household, not only do we have one device connected to the network, we actually have each person in your family, even the children, they also have cell phones. So everybody actually has multiple devices that need to access the network kind of at the same time. So as a result, the software itself are being kind of naturally also evolving too, to kind of meet the growth of the hardware, of the virtualization part, and basically take much better full advantage of the hardware and the firmware and all these advances. And then, of course, too, the impatient human beings are really making it more imperative, more urgent, that we have more systems that are built more catered towards us. And in a way, too, reactive systems, reactive programming, they are really meant to be for doing like event-driven programming. So they're event-based and non-blocking and asynchronous in nature, and being like very responsive. So now let's move on to talking about what is reactive. Oops. So first of all, I'll talk about the Reactive Manifesto. If you haven't heard about it yet, it's basically a set of guidelines and principles that define what reactive systems should be. And it's basically, if you go to this link, it's www.reactivemanifesto.org, it will describe all the details of the principles. Essentially, to summarize it first, too, is it promises more flexible systems that are highly responsive and more tolerant of failures, and also in how it handles failures, too. So that's kind of a highlight of it. But we'll go into the next slide and talk about what reactive systems, the principles are. And the latest version came out in September of 2014. So as such, too, it's being led by Lightband, the company that is led by Martin Odersky, the creator of Akka, as you may be aware of already. So now we move on to talking about reactive principles. So the first and foremost, one of the top principles, really, the systems needs to be very responsive. And by responsive, what it means is that all of the requests going into a system, they need to be able to respond in a very timely manner. Yeah, you can have a bit of wait time, but the wait time has to really be like more acceptable rather than taking a long time. So that's essentially like being very responsive. So the responsive systems also like focus on providing like really rapid and consistent response time, and then it also establishing like some reliable upper bounds too. So then they deliver a really consistent quality of service. And then that's responsive. The next thing we want to, oops, sorry, keep pressing the wrong button, apologize. Okay, so the next thing will be, let's talk about elasticity. So by elasticity, it means that systems needs to be able to scale up and down according to the load. So if you have more requests coming into the systems, then there should be either like more resources to handle this. They're basically essentially more resources to handle all of the requests. So a really good design like of a reactive systems would have that capability. So it allows for scalability, and not only that, it's essentially you allow a system not to suffer in the throughput. So the throughput should kind of remain the same despite the size of the load. Being very elastic also means that if your system is not under load, then resources needs to be returned back into like a pool, so then it can be used for something else. So that's elasticity. And then another principle is resiliency. So that's really like a very important also part of being reactive. Not only are your systems are responsive and being elastic, being resilient is really important because it also implies how you handle the failures. And from failures, you should be able to recover very gracefully, and the response time of handling failure also should not degrade as well. So that's resiliency. And how is it being achieved? It's basically by redundancy or replication or like being, that aspect of things. And also then, basically too. Also, one thing I want to point out is that the Akka system, which actually IBM has a partnership with Lightband, the Akka system, as some of you also may know, is that it has this supervisor capability in the actor model system. That basically, the supervisor provides really powerful capability of handling like recoverability of a system, which I'll also go into in a little bit too. And then another thing very important too in reactive systems is the message-driven capability. So that message-driven is essentially the enabler, because in our reactive systems too, we're talking about asynchronous communications of many different components that they're all running, by themselves or in a microservices, for example, environment. Then they are all like separated, all the components. So there's got to be a way of how you actually connect them together, and that's really being done by the messaging capability in the system. So that's message-driven. And I'll go into the next slide to talking a bit more about message-driven versus event-driven as well. Okay, but first of all, let me also point out there are some important distinctions too. So I use a picture of a fruit, because you're looking at fruit, they are really not the same. It looks like they are fruit, but likewise, reactive programming is not the same as functional reactive programming, even though there's some kind of usage in reactive programming that actually, and basically utilizing functional programming style, but they are not the same. And then, of course, to reactive systems and architecture, essentially is bringing reactivity to another level. So I'll go into that. But first of all, talking about reactive programming, the one really subtle kind of difference is that you have to understand the flow in reactive programming is basically any change in the state of the data within your system that drives the logic forward. Is events and then transforming the data that actually drives the logic forward. However, in functional reactive programming, in any programming you have a thread of execution. So your thread of continue going, then that drives the flow of a system. And then when we talk about reactive systems and architecture, that actually is another level up. So when we first of all, talking about programming, we deal with usually one component of a system that handles some internal logic and manages the data. But for reactive systems and architecture, we go above. We are kind of basically talking about a whole system that are consisted of many components, and each one of them are using like reactive style of programming, for example. So that's really, reactive systems architecture is the next level up. So because of such complicated scenario, all of them are functioning separately, and they're asynchronous way of kind of communicating with each other using like message-driven capability. So there also exists a need for ways of managing all of these components, so they kind of all function in a very consistent manner, essentially. So, okay. Oops. Why is it not moving? Okay, all right. So now I'll go into like comparing to like event-driven and message-driven. So for event-driven, by the way, this diagram too, I borrow from Lightbend's documentation. So I find it kind of useful because over here for event-driven, think of it as like a soapbox. So somebody making an announcement, think of it that way. So the events are being emitted like locally. But the events themselves, the message comes out, doesn't have an address, like telling it where to go to. It's basically up to the observers. So in reactive programming terms, right, we're talking about observables and observers. So it's up to the observers, those who are interested, basically, in a sense, it's like subscribe or listen and react to these events that are emitted by an event-driven system. And then when we talk about message-driven, then there's a difference because it's like two people talking in here. So they have the conversation, then the messages have a known target destination that it needs to go to. So essentially it has an addressable recipient and also a single purpose. So over here too, I've replaced them with some envelopes because it's like the old soap envelope, right? So they have an address where the messages are supposed to go to. So that's kind of important differences between the two. Okay, so now, before I go into talking about some more bit like concepts, I thought, well, I piqued the interest because as I started studying too, I'm thinking, well, what are some of the good use cases? So I was in Tokyo, the Java Users Group conference back in December, and in Tokyo, in Japan, there are many noodle shops. So I kind of wanted to kind of give a little bit of a hint of what I'm going to talk about in a few more slides. But for now, to think of like a noodle shop will be a good candidate as like to employ like reactive programming style or reactive systems approach to do it. And I'll explain in a few slides. So, okay, but first of all, we'll talk about reactive programming. Some of the common like patterns and terminologies. So by reactivity, we mean it means the process of responding to stimuli, external stimuli, and propagating events. And the events, they are really the stimuli that kind of like indicate stimuli some response to it, and then basically requires some change of data, like transforming the data during the process, right? The events happening. And then for streams, which is again very kind of also like fundamental building blocks, right? They're streams. So streams are primitive representations of a sequence of data elements. And for observable, that's essentially, they mean they are like stream of events. And the design patterns that are commonly used, they are observer pattern, composite, and iterative patterns, which I won't go into detail at this talk. Okay, so the next thing, we'll just explain some basic thing in reactive programming using this timeline. And I borrowed this from the Rx, the reactive extension, the Rx marble diagram. So in the very top part, when we talk about reactive programming, we're dealing with events in a timeline, in a stream. So in the very top one, this is just a line. So it indicates just a stream waiting for events to happen. And the second one, you see some different shapes, and those are the marbles, right? That comes in, they represent events. However, you get to this part, there's a perpendicular line. It means the stream has terminated in this case. And then the third one here, there are events that happen, and then there's like an X. So now, in reactive systems, kind of in that space, in that context, even like failures themselves are treated like first-class citizen. So unlike like traditional imperative style programming, in Java, we handle do try catch and taking care of what happened when exception occurs. But in reactive programming too, is that the events, like failure events, will be kind of like just like any other normal events. They come in the timeline as an event. But you also can be able to tell that it is some events of failure that needs to be handled accordingly. And then in the very bottom one is that these are events that are happening, but there's nothing else after the last marble. This indicates an open-ended stream, so it continuously be listening and listening for events to occur on this stream. So now let me go on to the next slide, which is talking about an example too of using an operator on a stream. So this is again just a basic example, just illustrate some basic. So I'm borrowing this RxJava, this call, this method operator map. So map is actually essentially, it does some data transformation, right? It's a functional style programming. So over here, using this timeline, then we have events that actually have data in here. That's 1, 2, and 3. So over here, we apply, using the dot map, we do some transformation, and we specify over here is, in this case, is 10 minus, or not minus, 10 multiplied by, the input multiplied by 10. So this is the map transformer. And after transforming, you see that 1 will be getting 10, and then 20, and 30 in this case. So in programming terms, right, so we're using like an observable, doing a dot just. So this is like taking in the input of, in this case, 1, 2, and 3, this example. And then basically you immediately apply the transformer to it, which is the dot map. And then you specify too, in this case, the function, what it does, 10 multiplied by x. And then immediately too, then the consumer that consumes the result is right here too. It's basically doing a dot subscribe. So the subscribe in here too, it basically tells it what to do, and in this case, it's basically printed out using Timber in this case, timber.d and print it out. So when you run this, then you see output item 10, item 20, and item 30 in this case. So one thing I want to point out is that for reactive programming style is a declarative style, as opposed to the traditional style that a lot of us, when we first started programming, are familiar with, right? That's imperative style, more blocking style. So here, too, the beauty of reactive programming is that you can actually have group like different, like the reactive, or actually functional style that's made possible since Java 8, the functional style programming, you can do that. Basically, you can group like multiple commands all together in the same single statement. So that's like the beauty of it. Because if you think of it, if you have to, like in traditional style, then you have to break out this whole set of commands into like multiple statements. So that's like one aspect of reactive programming. And as some of you may have heard from Venkat, who's like a big supporter of reactive programming. So this is like one big reason too that we should definitely learn about it, at least if you're not familiar with it yet, because it's just a lot more elegant. And also, too, over here, I just want to point out to you is that this is the link where I obtained this example, too. And there are many other examples where you can actually try things out interactively. For example, operators like flat map, doing filters, which is very common, too. So you can also try that out, too, if you like to. Okay, so now I then move on to talking about reactive systems design and some commonly used patterns too that I'll quickly go over. Here I won't have time to go very deep because reactive systems, if you get into the detail, it gets pretty deep too. But essentially too, I also there's a book called Reactive Systems Design that the author go into detail too, and it does a very good job of explaining all of the patterns. So essentially, it's broadly being categorized into 6 different patterns, like state management and persistent patterns, flow control, message flow. So state management and persistence, for example, like domain object, like sharding, event sourcing, those are more state management and persistent patterns, including like event streams. And then flow control patterns, you'll have like pull and manage queue and drop and throttling. And then there's also like message flow patterns too. That is like request response, ask pattern, forward flow aggregator, the saga pattern, for example. And then fault tolerance and recovery patterns, such as like circuit breaker, is one such pattern. And then in replication patterns, there are like active-active, active-passive, for example. And then there's also, which one I didn't say? Okay, so replication, that's what I talk about. And then, yeah, so those are like essentially some of the example too. And at the end of my slide too, I'll have a link where you can reference the Reactive Systems Design book where it goes into details talking about all the patterns. But here too, let me just highlight a few things. So in Reactive Systems Design, we're like talking about also like reactive microservices versus the monoliths. So everybody is probably familiar now too, right, with microservices. But there's also reactive microservices. So that, as such, is employing the asynchronous reactive style to microservices. And then essentially too, reactive systems, they, like one, if you think of it like that, we're dealing with the isolation of state, of space, of time and failure of any system. And then I want to just highlight a pattern to being used as circuit breakers. So that essentially is disallowing failure from propagating itself, right? If failure occurs, then it should have some circuit breaker mechanism that basically break it, stop it in there, take care of the failures before letting it kind of persist throughout the life cycle of your system. So that's circuit breakers. And then there's also back pressure too in reactive systems. So what it is, back pressure is that it's essentially any kind of system, right, processes scenario, you can have requests coming in, and then the back pressure buildup is when the too many requests coming in and the components are overloaded. So that builds up a back pressure. So in a very good design system, design of a reactive system, for example, like Akka too, it should have very good way of managing these back pressures. So then you probably, in an actor system like Akka, you start up more actors to handle these requests, or maybe you slow down the input, or maybe just put a stop on it and don't all come at once, that type of stuff. But most of the case too is that you probably want to increase the resources. So that kind of enable the elasticity of a system as well. And then there's also like high availability and eventual consistency. And I want to bring it out to a CAP theorem, if you're familiar with it too. What it says is that in any kind of data-intensive systems, you have 3 aspects, and that's network partition, high availability of the data, and also eventual, like data consistency, right, the integrity of your data. But the CAP theorem basically is saying is that of the 3 kind of makeup of this data-intensive systems, only 2 of the 3 can coexist in any time. And then network partition is always a given, it's always there, because it means that if your system is running, the network is connected. So given that, then basically either high availability or eventual consistency of data will have to kind of relax a little bit. So what in this case is that if you think of a reactive system is that the data needs to be highly available that meets the responsiveness requirement of the principle for any systems, right? So in that case, then data, the consistency of data may need to suffer a little bit which means sometimes if you query the data during the course of time, then the data comes back may not be accurate. But that's okay, because what happened is that the systems are being updated while you're querying it, but the update will keep happening. But eventually, this update will slow down. So when you slow down, if you keep asking for more data, then it should become consistent, is what this theory is talking about. So it goes into pretty deep kind of talking about it, too, in the reactive systems design. I just thought it's an interesting thing to bring it up, too, in a reactive systems. And the next two, I just want to point out about some standards in the reactive system space. That's the reactive streams. So reactive streams, essentially, it's a specification right now at 1.0, and it started by Lightband, and also then involved the other big players right over here. And it's essentially a standard for asynchronous stream processing with non-blocking back pressure. And the initial release was in 2015, and now the latest release is 2017. And basically, RxJava supports it partially because RxJava started sooner. That was before at Java 6. So did not have the functional programming yet at that time, right, in Java. But for Spring Reactor and also like Akka, it supports reactive streams fully. Oops. Okay. So now what about like microservices, right? So reactive programming is basically used within a single microservice, and that's used for implementing service internal logic, and also it manages the data flow. And for reactive systems, that's being used in between the microservices. So that's basically being used, reactive systems and microservices, to bridge all of the communications among the different components, right? So that then it enables all of the principles of reactive systems, namely responsiveness, resiliency, and elasticity. Now I want to also point out Lagom too. This is a reactive microservices framework from Lightband that's actually built on top of Akka, the Akka cluster, and also the Play framework, which is Play as the UI framework. And it's from Lightband, and it has a RPC-style programming. It supports RPC-style programming. And there's a message broker API that's implemented in Akka streams and Kafka. Also, the persistence is based on the concept of like if entities domain-driven design. So that has like event sourcing and CQRS, command query responsibility segregation. So I just want to point this out to you. Okay, let me see. Okay, sorry. So now I'll go back to my example of the Japanese noodle shop. So, so what happens is that in Japan, if you've ever been there in Tokyo going into a noodle shop, so basically, there's no server, physical person serving you. So there's one vending machine. So we all go in. So by computing terms, it's actually a very blocking kind of operation, kind of slow, right? So you go in and you use the vending machine to order your noodles. So everybody's waiting in line, one machine. Then you pay by cash. Then you get some tickets that has your order. Then you hand your orders over to your server. And the tables, there are no regular tables and chairs. They're all like, everybody sits around like a bar area, as you can see in here. So then basically you give your servers your order, and then you then have to stand in line. So can you imagine, I was actually there for some dinner and then waited for like 45 minutes. So in computing terms, think of it as a very blocking operation. You go in, order, wait in line. So you could be like as busy programmers like us, right? We never like to waste our time. We're still always thinking of good ways of doing our programming, improving. So instead of wasting time, actually we can use more of a non-blocking kind of approach. So that kind of, if we design a system like using reactive approach, that's probably something we can do. So then for me, I actually started scribbling too on a piece of napkin, and now I put it into like in my slide. So it's basically just a thinking, right? So it's kind of a primitive way, but it just gives you some idea. So basically, it's like I can use a mobile app. So instead, we're busy programmers, we sit there, do programming, and we're like, oh, we're hungry. Let's order noodles. So you download your app, right? You have your app installed on your phone. Basically, place your order. So when you place your order, it's like an order event happens. So that's an observable. So this observable is being observed by the observers, who are the waiters, waitresses, right? They take the orders. So they get it notified. They have some orders coming in. However, they can't really tell the cook to cook noodles yet, because they need to wait for the seats to open up because then we know we have limited seats. So then we need to also have another observables. Essentially, it's receiving events if there are open seats available. So in this case, the waiters would then have to kind of make sure that, oh, we have to manage 2 observables, and there are orders coming in, there are open seats. Once we can match up this, then we can tell the cook to start cooking the ramen. And in some sense too, I think we can also then have some mechanism of kind of automatically notify the customer, right, who has placed the order. So it's basically telling them, oh, your noodles are being cooked. So at that point, as busy programmers like us, we can actually say, oh, well, we should have the noodles ready in 10 minutes or 5 minutes even. So now let's compile a program or do something. Then we'll kind of go walk downstairs or across the street to the noodle shop. So then at the same time, your noodles being cooked, then another observables happen when you actually get your noodles cooked. And then you can then notify us, right, us, the customer. Then we get that, we are eagerly waiting. So this kind of, not like in reality, it's probably more complicated, but it's just a way of kind of like illustrating a way how we can do where we can make use of a reactive programming to implement it. So think of it in computing terms, and this is a lot more efficient. It's non-blocking. You place your order, go do something else, and then come back to it when things are ready. So that's kind of essentially the kind of purpose of doing reactive systems and reactive programming. Let me see how much time, okay. Okay, so now I go into the last part of my discussion, which is the discussion of the 4 commonly used Java tools and libraries. And first is RxJava. So RxJava comes out of Microsoft. Actually, I should say not Java. The reactive extension comes out of Microsoft. It started off with .NET. And then if you can go into this here, reactivex.io. So that kind of gives you more information about the reactive extension. So as such, it is very popular in mobile Android computing. For example, for Java, it's Android. So it is actually very popular because it's quite easy. You can just plug in your library and use it, right? And it's also ported to many language frameworks. So Netflix actually started porting it to Java in 2013, and the version 1 came out in 2014. That's pre-reactive stream specification. And in 2016, it comes out of Flowable and back pressure as well. So that came out, then. And then since then, too, it's been ported to JavaScript, so RxJS. And then there's .NET, started with that, and Scala, Clojure, Swift, and more, too. They have, the nice thing is that all of the APIs, the operators, they are similar, the APIs among all of the language frameworks support. And then here, too, just an illustration of a quick Hello World example of how to use RxJava, right? So if you look at in using this style, so in a Hello World, it's basically one command statement. So again, the reactive style is very efficient. One reactive statement, you use the flowable and then do a dot from array, takes your arguments, and basically do a subscribe right away. And then the subscribe essentially is the consumer of what's being processed. So it just do a system out print line, doing a hello world. So again, just pointing out too, is think of reactive programming. It's like you're grouping your server and client call kind of all in the same statement, in some sense, right? Because you're there, the producer is there, and your consumer will immediately consumes it. So. And the next thing, this one too, the code sample is basically not really a program, but just wanted to point out too, which I already pointed out earlier through the different example. Observable.just, it takes in, basically it's the input, the events, and then you have your consumer, that in this case is a system, simple illustration, right? It's just a system out print line. And then you can attach your producer to consumer by using an observable.subscribe and pass in the consumer. Okay, so next I'll go into the Spring Reactor. So Spring Reactor comes out of Project Reactor from Pivotal. And it is, the API itself is very similar to RxJava. And the reason is that here, right, David Connaught, who is the project lead on RxJava, he also contributes to Reactor too. So they kind of essentially two groups of engineers there is similar. They work into, on both libraries. So you find a lot of similarities between the two. But Spring Reactor is newer, And it started since Java 8, so it has a much more cleaner interface too. And then here too, I put a quote. David Carnot also was saying that to say that use Reactor 3 if you are allowed to use Java 8 or above, and then use RxJava 2 if you're stuck on Java 6 or need your functions to throw checked exceptions. So, and then here too, this whole list are all the libraries comes out of the Spring Reactor, but the core is basically the core library you use for building your reactive core reactive applications. And then you can see too, it also integrates very well, have other libraries, supports testing and integrating with Netty and Adapter and Kafka, RabbitMQ as well. Here too is an example of comparing between like traditional approach of Spring MVC and also the reactive approach. So you see that seems like they look kind of similar, like number of lines, but they kind of function, gets processed differently. If you look into the top one, it's a traditional approach using Spring MVC. You see that if you run it, then system output print line, traditional way will start first. Then the next call you go to will then make a call to get products. So in this case, this is a blocking call. So what will happen is that then your method basically is blocking, waiting for the results to come back, the list of products. And when it comes back, then it will then print out traditional way completed. And then it return the products and the method will end. Now, if you go take a look into the reactive approach using Spring Web Reactive with the web flux, over here too, you do annotations like get mapping here. And over here, I wanted to point out the text event stream value is basically it basically enables your Spring to turn this method into a source of event, and that's a server sent event, and I'll explain in a little bit. But otherwise too, if you go and run this method, then first you'll see reactive way using flux started. Then you make a call to do get product stream, and that returns a flux. So notice in here is that the flux itself, it's sort of like a ticket when you go to the store. You buy something and everybody's waiting in line. You get a ticket and wait to be serviced. So in some ways, this flux is kind of like that. Because the results won't get sent back to you. You get the stream. The result is sent back to you when it is ready. So in the meantime, you hold on to the flux. So the flux is basically then waiting for data to fill up. It's like the sync, right? Using the reactive like sync, right? That asynchronous way. The sync gets completed. Then basically it works like normal HTTP return. It returns the request back to your client. Now, if you say you want to use a more reactive approach to managing your response, then basically you can have your client subscribe. Earlier I mentioned about the server send event over here enabled by this annotation, this value. So you can actually make it a bit more reactive too by having your client subscribe to the event of receiving the server kind of, when it's ready, receive the response. And then in that case, then your client would then have to like basically subscribe to the event and then wait for the streams to come back of your data to come back too. Now that goes into a bit more detail, which I don't have time to go over. Plus there's also some concern too, if you're doing client-side subscribing to an event stream coming back, then you have to manage things if, when the session closed and all that stuff too, which I won't go into detail, but just want to point out to you, that's a way of basically receiving your response back in a reactive manner as well. So, okay, so going back to here, so when you run this function, get all, then basically when you get back your flux, then you actually see this reactive way using flux completed will actually show, because at this point it's a asynchronous call, so you're waiting for your result, but the method will exit at that point. Okay, so that's Spring Reactor. And here, too, is just a quick comparison, like a table comparing the two, which I've already talked about, so I probably won't need to go through all of it, but the idea is that there's similarities. They're single-threaded, non-blocking by default, and event-driven. And then the RxJava supports reactive streams partially, whereas Spring Reactor supports reactive streams fully. And then right now, RxJava 2 is at version 2, which actually have the flowable now, have the back pressure support. And controllers for Spring Reactor side is with Flux and Mono. So I have these slides made available to you too. So if you like to see this table in more detail. Okay, so now I move on to the next library, which is Akka. So Akka comes from Lightbend, and IBM has a partnership with Lightbend, and it's actually since June of 2017. And this is the link about the alliance. And Akka is basically make use of the actor model. The actor model is not new. It actually is based on Erlang. This Erlang programming language is an older style, from the 80s. But it's actually kind of very good, ideally, like built for more telecommunications applications, because as such, with telecommunications, like phone needs to be highly responsive. And also how it handles like the supervisor capability, all that too is actually come out of Erlang. Erlang has a pretty good way of handling failures scenario. And then as such, Akka, highlighting it is the event-driven capability, the location transparency, and being very lightweight, and the resiliency is really enabled by the supervisor capability. Here, so it's just a code sample of an Hello World. So over here, you'll find that in using Akka, it takes more coding. The reason is because of the actor model, right? So, but once you learn about it, then you realize the powerful capability of such. But here too, I still want to point out, right? So here is just a main method. And the main method is simple. What it does is basically start, it's just a small wrapper that around the generic launcher, the Akka main.main in here. So what this does is that it then starts constructing the main actor of this program. In this case, is the Hello World class. So, and here, let's take a look into the Hello World. So the Hello World in here, you see that it extends the abstract actor, but the thing is to notice that the pre-start is the part that is basically then start off the greeter actor in this case. So basically then it's basically, okay, so in this case, if you look into here, so it basically starts your greeter class, and then, over here then basically, let me see. So the greeter will then basically, if there's a command coming in, then what happens is that then the greeter gets started, but it doesn't do anything until there's some message that comes in and tells it to print out, what it's being called to do is basically print itself out, the name of itself. So over here, this is the greeter actor. So that's another actor, right? So basically, it starts up, it's basically sitting there waiting for messages to come in. And then basically, when it receives an order that tells it to print itself, then all it does is in here. And doing the receive builder here and .match equals, it is a greeting message it needs to print. Then it does system out, print line, hello world, and then basically print itself, and basically then it's done. So as you can see, it takes a bit more work in terms of coding, but it's, again, just a way of illustrating using the actor model. And next slide is that to kind of show this same implementation, but it's in Scala, which actually takes fewer lines of code. As you may be aware, too, Akka, again, is from Lightbend, and it's started by Martin Odersky, creator of Scala. So naturally, too, Akka started off supporting only of Scala. Then later it gets support into like Java. So Scala is kind of like the natural language for Akka, the whole Akka framework. So. Okay, so then I don't have as much time left, so I go into talking about VertX. So VertX comes from Eclipse, and it's a very flexible polyglot framework that interoperates with other library tools and frameworks too. So in other words, you can actually have VertX, and then it's capable of, you can call a JavaScript library calling Ruby. That's all capable too. So that's a very flexible framework. It's also very newest library, set of libraries among all four. It doesn't use the actor model, but it uses a model called verticals. And verticals are similar in actor too. But what it does is that there are components that are being deployed and executed by the VertX engine. And we have, it's very event-driven, and it runs only when it receives a message. And also there's the VertX event bus that handles all the events. And the nice thing, again, is not restrictively tied to any container. So your VertX libraries can interoperate very well with other libraries as well. And here is an example of the Hello World. So again, it's also, you can tell too, it's also pretty efficient, elegant too. So over here, you doing a hello world, you can do a vertx and then basically .vertx again starts your vertx engine and then do a .create HTTP server. And then you basically do a .request handler and pass in your requests and then your response, all done within a single statement. And basically over here, it's basically when it ends, it has the hello world. And also then you also do the .listen, which binds this HTTP server listener, binds it to port 8080 in this case. So you can tell too, actually, vertx is becoming quite popular too, as I'm aware of, because of how easy it is to kind of like get started, essentially, and also how it can interplay very well with other languages and framework. Okay, so I guess with this, I only have like 2-3 minutes left, but I do want to thank you. Actually, no, here first. It's just a recap and takeaways. So some of the things I already talked about, maybe I won't go over, but just wanted to point out if you're new to doing declarative reactive programming, don't feel like it's too confusing. That's actually, that's how I found it. Found at first too. But it takes some time, so once you get used to it, it's actually you appreciate how elegant it is, and you should definitely like learn about it. And Venkat also made the statement about reactive programming being like the next paradigm, that we should be aware of, or at least like learn about it too. And then all these I already talked about, right? It's overloaded word, and it's confusing, but it's not the same, right? Reactive programming and functional reactive programming. Okay, so some of the benefits being more elegant, the programming style, and reactive systems architecture will bring reactivity to another level. So I encourage you, if you're interested, read into the reactive systems design, read into it more, because it's really, the Lightband, that company, they have very amazing engineers that kind of very brilliant, some of the concepts and principles that they can implement in Akka too. Okay, so last but not least, it's basically I want to point out too, reactivity to this day has not been fully realized yet. Because, why? Because if you think of any systems, strictly speaking, if you call a systems reactive, then in your layers, many layers of connection in your whole stack, every part of it needs to be reactive, needs to have non-blocking I/O. However, in today's world, we all rely on a relational database, especially. None of the relational databases support like NIO, non-blocking kind of communication yet. So when you get down to the database, even though today we have Pivotal, we have a library called R2DBC, for example, that's a reactive database connectivity library. It's only done on the connectivity level. You have NIO, non-blocking. But when you get down to connect to the database, and the database itself goes back to the blocking way of making calls. So that's something I want to point out too. So, and it's been interesting. I also, myself too, have been trying to figure out, would that ever be database, relational database, maybe using like non-blocking I/O? So that's a question I'm waiting to ask some of these experts, for example, like say, the big database manufacturer, like our Oracle, for example. So actually, I'll also be planning on running a virtual reactive user group. So if you follow me on Twitter, maybe I'll watch for me, because I'm still trying to set that up. Then I'll be interviewing folks, like say, from the different vendors and talking about subjects like that, what will be happening. So that's database kind of level of non-blocking I/O support. One question I'll be asking too. And here, it comes to an end now. So thank you very much for coming to my talk, and this is how you can connect with me. I encourage using Twitter. Usually I use Twitter a lot too, and then my GitHub and my developer profile on IBM. And this too, I want to invite all of you, if you're interested too, please sign up for the IBM Cloud. It's actually, we have a free tier access to. So this is the tiny link, the IBM Biz, this thing. So you sign up for it, and you get a free tier access for life too. And of course, not everything underneath the IBM hood, but IBM is very strong supporter of open source technology. So you'll find, for example, like Cloudin is a NoSQL database. You can have access to the basic tier without paying for anything. So it's pretty good, and there you can build things. There's IBM Watson, the AI, the machine learning part, a lot of resources too. So I invite all of you to sign up for it. It doesn't cost you anything. And then also these are links about the IBM Alliance with Lightband, and the Reactive Manifesto, as well as this book that written by this specialist in reactive systems called reactivedesignpatterns.com. Yeah. And also invite you to wait for, and checking out the developer.ibm.com Technologies Reactive Systems. We'll be like adding more blogs and articles and tutorials, and also my virtual reactive user group that I'll be starting with my colleagues too. So please watch for that. And then one more thing is that I want to invite you to also check out, this is a global hackathon event, if you are not already familiar with it, by IBM with some other organizations. And if you visit this link, callforcode.org, it will tell you how you can enter it. It's a global hackathon. It's for very good cause. It's for natural disaster preparedness. It calls for your creativity. And there's a really good prize money associated with it too. And also, too, if you have local city, I'm not sure, maybe in Krakow, but some other cities, they have actually meetup groups that people get together and do this call for code. You can enter this competition on your own, or maybe form teams of up to 5. So call for code, and then there's still time open until July 29th. So I invite all of you to also check that out. And then I think with that comes to an end. So I want to thank you again. Thank you everybody for coming to my talk, and I appreciate all of you being here. And also please send me questions and feedback, and tell me how I can improve or make the talk even more interesting next time. I hope to come back again too. I really love Krakow. So thank you very much. Yeah.